Previous videos were about what is called electrostatics. It was primarily about charges that are in equilibrium. In the upcoming videos, though, we'll be primarily analyzing the motion of charges in conductors. Conductor materials themselves are made up of very large numbers of positive nuclei as well as negatively charged electrons. Many of the electrons are bound to the nuclei and cannot really move much, but some of them are free to move. Those electrons which are mobile are often called conduction electrons or free electrons. They may also be called charge carriers. Below is a simplistic picture of charge carrier electrons inside a conductor. This could, for example, be a section of a cylindrical shaped wire. Delta X stands for the length of a particular segment of that wire. In this situation, delta V doesn't stand for a potential difference, but it instead stands for the volume of a section of wire. Capital N will stand for the number of free electrons in a given volume of a conductor. Little n is reserved for the free electron density, and the units of that will be electrons per meter cubed. The free electron density varies quite a bit among different materials, and there are tables which can tell us the free electron density of various materials. Before we start analyzing the flow of charges, it's useful to consider what happens before current flows. Are electrons in a metal wire moving, even if there's no current in the wire? The answer to this question is yes. The kinetic energy the particles possess will be related to the macroscopic temperature of the conductor. The higher the temperature, the more kinetic energy the particles have. And the particles can have vibrational, rotational, and translational kinetic energy. Below is a picture of the motion of an electron within a conductor. What can happen is it can move around at random, and we can also see that the electrons can bounce off of particles and be redirected due to Coulomb forces within the conductor. You may be surprised to know that the free electrons in a conductor will move with average speeds on the order of 10 to the 6 meters per second. So that's 1,000,000 meters per second. So electrons are actually moving very quickly inside room temperature conductors. Closing a switch that connects a conductor to an energy source, such as a battery, will actually set up an electric field inside the conductor, and that will push the charge carriers through the wire. It doesn't mean that every electron is going to move from negative terminal to positive terminal in the circuit. There will be a lot of random motion, but what we will see is, statistically, on average, the electrons will tend to drift opposite the electric field. So, for example, if you have a battery and some kind of circuit here, we'll have negative charges all throughout the metal. This is going to be our negative terminal, and this is our positive terminal. Inside the wire, an electric field will be set up. Now remember that our electric field points conventionally from positive to negative. But this is not the direction that the electrons will tend to go. They're going to tend to go against the field. So if we zoom in here, Not every electron is going to move exactly 180 degrees opposite the field. It'll actually bounce around quite a bit. But what we see is that on average, they tend to drift against the field. Recall what it's like to flip on the light switch in a house. The lights come on nearly instantaneously, don't they? How fast do you think charge carriers move on average through a conductor in a typical house circuit? It's actually a common misconception to think that electrons will, on average, flow very fast through a typical circuit. Contrary to common belief, the majority of electron charge carriers don't flow quickly from a battery to a light bulb, for example. They will actually drift very slowly through the wire. This speed is called the drift speed, and it's given the symbols V sub d. What will happen is particles will drift like a slow-moving river everywhere in the circuit. That doesn't mean that all particles move slowly, though. Some can rearrange quite quickly. And so what we will see typically is electrons on the surface of the wire will rearrange very fast. But the electrons inside the wire are the ones that tend to drift slowly. The drift speed formula is the same as the Physics 1 formula for speed. It is delta x over delta t, where delta x stands for the displacement of a charge carrier. But drift speed is not the speed of any one particular charge carrier. It is instead an average trend that is observed in the random motion of particles. The picture below shows an electron drifting against the electric field. Even though its instantaneous speed may be very fast, on the order of 1,000,000 meters per second, the drift speed is quite slow. Let's look at the definitions of current and electron current. Current is given the symbol capital I, and it's the flow of total charge Q through a surface per time. The surface could be just a cross-section of a conducting wire, for example. The unit of current is amperes, which is symbolized by capital A. Electron current, however, has the symbol little I, and little I is the flow of charge carriers per time. And in this case, we use the number of carriers divided by time, whereas for current, we would put total charge Q over time. All right, question A says, use the formula to find other units that are equivalent to amperes. So current will be given in amperes, but this is equivalent to a coulomb per second. What would be the units of electron current little I, though? Well, little I has a number of electrons divided by time. So sometimes this is expressed as electrons per second, or even in some cases s to the negative 1, which is just a number of particles per second. And that is the same as 1 over seconds. Sometimes the electron part is left out. We want to find a formula that relates current I and electron current little I. For this, we can use our formulas from the past. One of them would be that Q equals big N, a number of electrons, times E. Okay? Alright, so one technique we have for finding relationships between two different formulas will be to take the things that they have in common and solve for those constants. So we would get delta T equals delta Q over I. And over here we'll have delta T equals N over little I. Now we see that this delta Q over big I is equal to delta T. And big N over little I is also equal to delta T. Therefore, we could set them equal to each other. After cross multiplying, we would get this. And if we replace Q with NE, we'll get I times N times E equals big I times N, and the N's will cancel. We're left with the formula I times E equals big I, or it could be written as I equals big I over E. So these are formulas we can use to convert between current and electron current, where E stands for the elementary charge of the charge carriers.